All right, well, welcome back for another deep dive with us. And today we're going to be looking at something pretty fundamental to how our planet works.
Yeah, some might even say the foundation.
Yeah, so today's topic is Plate Tectonics Theory, which you've no doubt heard of. And we're going to explore how exactly the Earth's surface is made up of these moving pieces.
That's right. We're going to be diving into the core concepts of this theory and really trying to understand the forces that shape the Earth.
And it's pretty incredible when you think of it, right? Like these slow movements over millions of years create these huge mountain ranges, vast oceans, and
Even earthquakes.
exactly, and it's all part of this continuous reshaping of our planet.
And we'll also touch upon how this theory came to be accepted. It wasn't always a given.
Right, it had its share of doubters in the beginning.
Oh, absolutely. There was a lot of resistance to the idea initially.
So like back in the early 1900s, there was this scientist named Alfred Wegener.
Oh, yes, Wegener.
He came up with this idea of continental drift.
Right. He proposed that the continents were once all joined together in a supercontinent called Pangaea.
Yeah, like a giant jigsaw puzzle, and they slowly drifted apart over millions of years.
Exactly. And he had some pretty compelling evidence, too, like the way the coastlines of South America and Africa seem to fit together, and also the matching fossil records on these different continents.
That makes a lot of sense, but then why wasn't his idea immediately accepted?
Well, the problem was he couldn't explain how these massive continents could actually move. What was the mechanism driving this drift?
So they needed more than just the observation, they needed a scientifically sound explanation.
Precisely. And that's where the skepticism came in.
I see. So when did things start to change?
Well, it wasn't until the 1960s, with some major advancements in our understanding of the ocean floor.
The ocean floor, okay.
Yeah, things like the discovery of seafloor spreading, where new crust is formed at these underwater mountain ranges called mid-ocean ridges.
Okay, and how did that support Wegener's idea?
Well, scientists found these symmetrical magnetic patterns in the rocks on either side of these ridges.
Magnetic patterns.
Yes, and these patterns basically showed that the seafloor was spreading apart over time, like a giant conveyor belt.
Wow, so it was like the Earth itself was leaving a record of its movements.
Exactly. And this evidence, along with other findings about the Earth's interior, finally provided the mechanism that Wegener was missing.
So that's what led to the development of the modern plate tectonics theory.
Exactly. It all started to come together.
So our mission today is to help you listening really grasp the core concepts of this theory.
We want to go beyond just knowing that the Earth moves. We want to delve into how it happens and why it matters.
All right, so let's start with the basics. What exactly are these tectonic plates?
Okay, so imagine the Earth's outermost layer. The lithosphere is broken up into these massive slabs of rock.
Like puzzle pieces.
Exactly, and these pieces are called tectonic plates, and they're constantly moving, albeit incredibly slowly.
So how slow are we talking about here?
Well, it's often compared to the speed at which our fingernails grow.
Wow, that is slow.
But even though it's slow over millions of years, these tiny movements add up to have huge effects.
Right, like creating mountains and oceans.
Exactly. It's all about this gradual but continuous reshaping of the Earth's surface.
And what drives this movement?
Well, it all comes down to heat from the Earth's interior.
Okay, heat. So how does that work?
So this heat creates these convection currents within the mantle, which is the layer beneath the crust.
Convection currents like in a pot of boiling water.
Exactly, and these currents exert forces on the plates above, causing them to move.
Interesting. So it's like a giant engine deep within the Earth driving all of this activity.
That's a great way to put it.
So we have these plates moving around, but what happens when they meet at their boundaries?
Well, that's where things get really interesting because that's where we see the most dramatic effects of plate tectonics.
Okay, so let's talk about these plate boundaries. What are the different types?
So there are three main types: divergent, convergent, and transform.
Divergent, convergent, transform. Got it. What happens at divergent boundaries?
So at divergent boundaries, the plates are moving apart from each other.
Okay, and where do we typically see this happening?
The most common place is at those mid-ocean ridges we talked about earlier.
Right, those underwater mountain ranges?
Yes, so as the plates pull apart, magma from the mantles rises up to fill the gap.
Magma that's molten rock, right?
Exactly, and as this magma cools and solidifies, it creates new oceanic crust.
So it's like the Earth is constantly making new land at these divergent zones.
Precisely, and a great example of this is the Mid-Atlantic Ridge.
Oh yeah, I've heard of that.
So along this ridge, the North American and Eurasian plates and also the South American and African plates are slowly pulling apart.
And new seafloor is being created in between.
Exactly. So the Atlantic Ocean is actually getting wider over time.
Wow, that's pretty mind-blowing to think about.
It really is.
Okay, so we've got plates moving apart. Now, what about convergent boundaries? What happens there?
So convergent boundaries are where plates collide with each other.
And what happens depends on the type of plates involved, right?
Exactly. There are a couple of different scenarios.
Okay, so let's break it down. What happens when an oceanic plate collides with a continental plate?
All right, so oceanic crust is denser than continental crust. So when they collide, the denser oceanic plate gets forced underneath the continental plate.
Underneath.
Yeah, it's a process called subduction.
Subduction, so one plate is diving beneath the other.
Exactly, and this creates some pretty intense geological features.
Like what?
Well, for one, as the oceanic plate sinks down into the mantle, it heats up and releases water.
Okay.
And this water lowers the melting point of the surrounding mantle rock, which creates magma.
Magma again?
Yes, and this magma then rises up to the surface and erupts, creating volcanoes.
So that's how we get volcanic mountain ranges.
Precisely, and we also see the formation of deep ocean trenches, where the oceanic plate is bending down into the mantle.
So trenches and volcanoes all from this subduction process.
Exactly. It's a pretty amazing interplay of destruction and creation.
Yeah, that's a good way to put it. And do you have an example of a place where this is happening?
Sure, a classic example is the Andes Mountains in South America.
Oh yeah, those are impressive mountains.
They are, and they were formed by the Nazca Plate subducting beneath the South American plate.
So the Nazca Plate is the oceanic plate.
That's right, and the South American plate is the continental plate.
Okay, that makes sense. Now, what happens when two continental plates collide?
Well, in this case, neither plate is dense enough to easily subduct.
So they both kind of resist going under.
Exactly, so instead they just smash into each other with incredible force.
And what happens then?
Well, all that force causes the crust to buckle and fold upwards, creating massive mountain ranges.
Like the Himalayas.
Exactly. The Himalayas are the highest mountain range on Earth, and they were formed by the collision of the Indian and Eurasian plates.
So it's like two giant bulldozers pushing against each other, and all that earth and rock just gets piled up into these towering peaks.
That's a great analogy.
Okay, so we've covered divergent boundaries where plates move apart and convergent boundaries where they collide. Now, what about transform boundaries?
So transform boundaries are where plates slide horizontally past each other?
Horizontally, so they're not pulling apart or pushing together. They're just kind of grinding alongside each other.
Exactly, and this grinding motion isn't always smooth.
What do you mean?
Well, the plates can get stuck due to friction.
Stuck.
Yes, and as they try to move past each other, stress builds up.
Okay.
And eventually that stress becomes too much, and the plates suddenly slip, releasing all that stored energy.
And that's what causes earthquakes.
Precisely. It's the sudden release of energy that makes the ground shake.
And a classic example of a transform boundary is the San Andreas Fault, right?
Exactly. The San Andreas Fault is where the Pacific Plate is sliding past the North American Plate.
And that's why California has so many earthquakes.
Precisely. It's all due to this ongoing movement and the periodic release of stress along the fault line.
Okay, so we've got plates pulling apart, plates colliding, plates sliding past each other. It's a pretty dynamic system.
It really is, and it has far-reaching consequences for our entire planet.
In what ways?
Well, for one, plate tectonics plays a crucial role in recycling the Earth's materials.
Recycling, how so?
Well, at subduction zones, old oceanic crust is being pushed back down into the mantle.
Okay.
And over time, this crust gets melted and reintegrated back into the Earth's interior.
So it's like a giant recycling plant.
Exactly, and at the same time, new crust is being generated at divergent boundaries.
So it's a continuous cycle of creation and destruction.
Precisely. And this cycle helps keep our planet geologically active and dynamic.
And it's not just about the physical Earth, right? Plate tectonics also affects life on Earth.
Oh, absolutely. The movement of continents over millions of years has had a huge impact on the evolution and distribution of plant and animal species.
How so?
Well, for one, though, that's changed global climate patterns by altering ocean currents and atmospheric circulation.
Okay. I can see how that would be a major factor.
And the formation and breakup of supercontinents has also played a role.
By separating and connecting land masses.
Exactly. This has led to periods of both isolation and connection, which has driven the diversification of life on Earth.
So different species have evolved in different ways depending on their environment and how connected they were to other populations.
Precisely. It's a fascinating interplay between geology and biology.
It really is. So to sum it all up, plate tectonics theory is this incredibly important framework for understanding how our planet works.
It explains so much about the Earth's features and processes.
From mountains and oceans to earthquakes and volcanoes.
And it all stems from these incredibly slow but relentless movements of the Earth's tectonic plates.
It's almost hard to grasp the timescales involved millions and millions of years of these plates slowly shifting and reshaping our world.
It really puts things into perspective, doesn't it?
It does, and it makes you realize just how dynamic and ever-changing our planet really is.
Absolutely. So, for all of you listening out there, I want you to take a moment and consider this. How can something so slow and seemingly insignificant, like the movement of tectonic plates, have such a profound and lasting impact on our planet?
It's a question that really makes you think about the power of these geological processes that are constantly shaping the world around us, even if we don't always notice them.
It's a reminder that our Earth is constantly evolving and changing, and we're just along for the ride.
And that's a pretty amazing ride, if you ask me.
I couldn't agree more.